So in this video, we're going to talk about electric circuit, charge and current. So what is an electric circuit on an electric network? Electric circuits or network is composed of several electrical elements. We will define later what we mean by electrical elements. But one of these elements are the battery or the source of the electrical circuit and resistors. Now let's say I connect these two elements by a copper wire or a conductor such that current can flow through the uh, from the source going to the resistor. So now I have an electric circuit. So the uh, the important part here is that we need to have a closed path in order to classify the circuit as an electric circuit. Without a closed path, we cannot call it an electric circuit. Now, sometimes we hear terms like electric network, and they are sometimes interchangeably used with electric circuit. Um, the, the 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 main difference here is that when you talk about electric network, usually we're talking about several closed paths. So, for example, if I cut the wire somewhere here, that means that it's not anymore an electric circuit because the flow of current is cut off. Here is a very simple circuit. So we have here a lamp connected to a source, so it's a battery. And as you can see, current is flowing towards the lamp and back to the battery. Now, shown here also is the flow of electrons because current is really the flow of particles. We will discuss that more in detail when we go to the next slide. So this is a very simple circuit, and uh, your flashlight, the one we use in households, is actually constructed this way. So, well, uh, without the switch, of course, as shown here, so there's no switch. But basically, the flashlight is constructed this way. Okay, so let's go to electric charge. Um, so we've been talking about current, and current is really the flow of electrons. Now, for particles, and to be specific, it is the flow of electrons. Now, particles has a property called a charge, and for an electron, it has a charge of this much, so it's a very small number, measured in the unit called coulombs, or in this case, the symbol is capital letter C. Now, so an electron has a charge, and in fact, it is a negative charge, and it has, in terms of coulombs, it is a very small number. Now, to make one coulomb, or specifically -1 coulomb, you would need a very large number of electrons, this much. Now, uh, the unique feature about an electric charge is that they are mobile. So what do you mean by this? So uh, take note that in your physics days, you learn the the atomic structure, and in that structure there is a nucleus composed of protons and neutrons, and around it orbits electrons. Now these electrons, in uh, in its stable state, these electrons go around the nucleus. Now, if this atom is bombarded by an external energy, a good example of that is, for example, heat. So, for example, you have a material and you heat it up. The tendency of these electrons is that they are knocked from their orbits. So, in such case, they roam around the material, jumping from one atom to another. Now, since these electrons are possess a charge, as we have discussed a while ago, that means if these electrons are roaming in, let's say, a material, that means we have a roaming charge, and that is what we mean by a mobile electric charge. Because once these electrons move around, we have a mobile electric charge. So they can be transferred from one place to another, and they can also be converted from to another form of energy. So now, of course, what makes these charges move in a material? Of course, later we will talk about electromotive force, which is actually the driving force that makes these electrons move around, or uh, that creates the moving charges. Now, when charges starts to move, or we have a motion of charges, we have what we call an electric current. So for example, I connect a conductor, I make a circuit, I connect a conductor to a battery. Charges starts to move because the electrons in the conductor gets knocked off in their orbits and starts to roam around. That creates a moving charge. That creates the electric current. So the thing here is that if we have moving charges, we have current. Now, by convention, the electrons moves from the negative terminal of the source from here, that direction. But by convention, we define current to be in the opposite direction. So current is in this direction. Uh, so let's make a more formal definition of electric current. So from the book of Alexander and Sadiko, electric current is the time rate of change of charge, so measured in amperes. So current is really the rate of change of charge. So this is rate of change of charge. So it measures the flow of charges per unit time. So uh, if the flow of charges is fast or high per unit time, we have a high current. So we have a higher current. Another definition from the book of Dorff and Subowoda, electric current is time rate of flow of electric charge past a given point. So, for example, here you have a conductor, and this is a some point in the conductor, and you take a look at the flow of charges here. If you measure the time rate of flow of this charge past this given point, you're actually measuring the current. So the higher this flow, or uh, the higher the flow, you will get a higher current. Again, take note that if this is the direction of the flow of the electrons, current is in the opposite direction. Okay. So as I mentioned a while ago, current uh, um, is by convention opposite to the flow of the electrons. Now, in the left figure, we have here uh, two representations of current flow. So, for example, this is a wire, and current is in this direction. So you have 5 amperes there. We can also draw that to flow in the opposite direction, provided we change the sign of the flow, or the figure. So instead of 5 amperes, we put a negative sign there. So these representations are actually equivalent. Now we have different classifications of current. We have direct current, and we have alternating current. Now direct current means, or sometimes we call it DC for short. Direct current means that the current remains constant. It does not change with time. So what we mean by constant is that the rate of charge flow is actually a constant. And alternating current is the rate of flow of the charges per unit time is changing actually. So call it alternating current. Now there are to be more specific, we have if we graph the direct current, it would look like this. Now for the alternating current, we uh, we have actually several representations of this. Uh, in fact, as long as the current is changing, we have what we call an alternating current. So here we have the ramp. So the current just keeps on increasing with time. And we also have the exponential. So in this case, current starts at the high value, but it decreases with time. Now we also have a what we call a sinusoidal current, and it it looks like a sine function. Uh, Now a sinusoidal current is what is actually used in the industry, and we will talk more about this, especially when we go to circuits 2. Now, by the way, I've mentioned that the unit for current is amperes, and this is really equals to coulomb per second. So this is the basic unit of current, coulombs per second. An ampere is just a derived unit. That means 1 coulomb per second. So 1 ampere means 1 coulomb per second. So we've been talking about electric charge and electric current, and we said that current is really the rate of flow of electric charge. So therefore, mathematically, we can represent current in this manner. And if we reverse it and get the integral, or we solve for q, that means that we have this equation. So q can also be expressed in terms of the integral of the current from uh, a specific time. So let's say t sub 0 up to another specific time. So this equation really gives us the amount of charge that flowed between these two time time points. So t sub 0 and t. So actually, what we get here is really is the delta of q, because that is the amount of q that has, or the charge that have flowed between these two times. Now we have another formula here, and this really means that this is the total q. So this is actually the total q that flows, that uh, has crossed a given point in a material or conductor, let's say. So this one is the existing charge that has already crossed before time 0, and we're just simply adding this. So well, this one is like that, and we add this, so we get the total. Now, when we talk about varying quantities of current and charge, we usually use smaller or small case. But when you talk about constant quantities, we normally use upper cases. Now let's go through a few examples of what we've been talking about. So current and charge. So in this example, we have an element, and through the element, charges are crossing in this direction. Take note that means that current is in this direction. So charges are flowing on the left direction, and it is given by this expression. Now we're asked to find the current after 1 second. So this is actually the solution. I'll just flash it. So let's go over with the solution. So since I can be expressed in terms of the rate of change of the charge that crosses a given point, so that means that we can get the current by simply getting the derivative of this expression. So that is shown here. So it's 20 e to the minus 2t millicoulombs per second. Now, so we get this final value for the current. Now take note that if we graph uh, Q, it would look like this. So this is Q here, and this is T. So it starts from 0, and it rises to a constant value, 10 millicoulombs. Now, for the current, however, it starts high. So this is I, and this is 20 here, and then it decreases and approaches 0 as time approaches infinity. So that is how the current behaves when the charge starts to go constant. The current actually becomes 0, because the slope, or the dq dt of q, is 0. So as shown here. So if we substitute t equals 1 second here in the equation for I, or the expression for I, what we get is 2.7 milliamps. So it's maybe somewhere here. So here is your 2.7 here, and this should be around 1 seconds. Now let's go to the next example. Now in this problem, uh, so let's say we have here a wire, and again charges is flowing. So let's say in this direction. So this is a given point, and charge is flowing. And again, we know I to be flowing in the opposite direction. But Q here is not given as an expression, but given as a graph. So as you can see here, it starts 0, and then between 0 and 2 seconds, it increases constantly at a constant rate, and then past 2 seconds until 6, it decreases at a constant rate here, and again it increases after 6 seconds. Okay, so how do we get the current given this graph? So we don't have an expression, what we have is a graph. So let's go to the solution. So to plot the current, let's plot it side by side with Q. So on the right side, we have the scale for I, and for Q on the left side. So take note that um, we already said that I is really just the time rate of change of Q. Okay, is the dq dt here. And in order to plot I, we simply need to check the slope of Q. So let's check the slope of Q based on the plot of Q. So for example, between 0 and 2 seconds, we observe that the plot of Q is this one, and it has a constant slope. That means the your I there, the current between 0 and 2 should be a constant, and must be equals to the slope. So that is 50 divided by 2 seconds. So that will give you 25 amperes. So, so we have 25 here, and we have between 2 and 6 seconds. We observe again that this is the plot of Q, and it has a constant slope as well, but this time it is a negative slope and equal to 100 divided by 4 seconds. So that will give you negative 25 because of the negative slope. And then between 6 and 8 seconds, the slope again is positive, like that. And in fact, the same as this. And therefore, that will give you again a positive 25 amperes, like that. So finally, the plot for the current would look like this. So, so this one, and then it goes down immediately after 2 seconds there, and then after 6 it immediately rises to a constant 25 amperes. Okay, so take note that we're talking about a wire here, and charges flowing past a given point. So let's say this is point A in the conductor or in the wire, and let's say we observe the amount of Q that is crossing point A. So starting with 0 seconds, it crosses and going to the left direction. And let's assume that to be positive. So it means that Q starts to the amount of Q that is crossing going to the left is actually increasing. So increasing. Then after 2 seconds, you notice that the amount of Q that crosses is decreasing, or the net Q that crossed is decreasing. So that would only mean that uh, Q must be flowing on the opposite direction. In order for Q to decrease from 50 going down to 0 here. So so after 4 seconds, the net Q that actually crossed point A is a 0. So that means that the amount of charge that crossed between 0 and 4 and the amount of charge that crossed going to the right must be equal, and therefore the net charge that crossed point A must be 0. So that is what is meant by that. So that means between 2 and 4 seconds, Q is actually flowing on the right direction. And that means that current is flowing to the left direction between 2 and 4 seconds. And of course, that means that between 0 and 2 seconds, current was flowing on the right direction. And after 4 seconds, Q continues to flow on the right direction and up to the 6th second. And after the 6th second, Q again starts to rise. So therefore, that means that after 6, Q must again be flowing on the left direction. And that means I there must be on the right direction. So that is what is meant by this graph here. And again, to get the plot of I, we simply observe the slope of Q, and that's it. That is how we solve the problem. And finally, let's have our last example. So in this example, we have an element, and this is the plot of the current, this one. So this is the plot uh, um, of the current to the element. So if you observe, the current starts is a constant between 0 and 1, so it's 10 amperes, and then it slowly or constantly decreases between 1 and 2, then again it becomes constant between 2 and 4 seconds, and finally from 4 to 5 it decreases until it becomes 0. So the question here is, what is the total charge that passed through the element after 1 second, 3 and 5 seconds? So let's check out the solution. So this is the solution for example number 3. So we have here an element, and let's assume that the current is flowing on the right direction, and so that would mean that Q would be to the left. Now take note that the plot of I is all positive. That means I is always on the right direction, and Q is also on the left direction between 0 and 5 seconds. Okay. Again, as discussed previously, we note that we said that Q is really just the integral of I dt um, between, let's say, time t sub 1 and time t sub 2, something like that. Okay, so well, integration means simply that uh, we're trying to sum up things here. So in our case, since we have a plot for I, this formula really means that we're just really taking the area that is subtended by I with respect to the horizontal axis. What is meant by here is that, for example, if we ask ourselves after 1 second, what would be Q? Okay, so assuming that before zero, Q there is zero, so we ask ourselves what is Q after 1 second. So that would be the accumulation of charges uh, between 0 and 1 second, and that would really mean uh, the area of this part here, that would be the integral of Q of I from 0 to 2. Okay, so therefore to get the Q after 1 second, that would mean that we simply get this area. So that would be this one. So here, somewhere here, and that is equals to 10 times 1 second. So that will give us 10 coulombs here. And then we also get the accumulated charge after 2 seconds. And that would mean that we add this area to the previous area. Okay, so that will give us that. So this area plus this area, that will give us 17.5. So it accumulates because this area are both positive. That will give us this point. And after 4 seconds, so let's go up to 4 seconds because current there is constant. After 4 seconds, that would give us 27.5 coulombs. So that will be the previous area that was summed up plus this area, that will give us 25.5. And after 5 seconds, we again add this area, and that would give us 30 coulombs. So this will be the points. This will be the points. So after 1 second, that is our charge accumulated. After 2, after 4, and after 5 seconds. Okay, so how do we plot this Q given these points that we have? So again, we observe the behavior of I. Let's say we start between 0 and 1 second. So the that I here is a constant. So that would simply mean that the slope, Q should be sloping with a constant value. So that would simply mean that Q would be a straight line, okay, because I is a constant value, And also between 2 and 4 seconds, I is also a constant. So that would mean that the slope of Q there should also be constant, something like that. And now between 1 and 2 seconds, take note that I is decreasing from 10 to 5 amperes. So that would mean that the slope of Q must be decreasing from 10, which is this slope, okay. Uh, so that will only mean that the curve must look something like this and connects the curve between 2 and 4 seconds. And again, between 4 and 5 seconds, that would also mean that the slope must decrease from 5. So this is this slope. This is 5 actually. And when at 5 seconds, that slope should be 0 or should be horizontal because current there is a 0. So, so that is the plot for I. Now, we don't, it's not any more important and it's not required in the problem to get the equation for the plot, but take note that this equation must be a straight line and also this one, and that can easily be determined, while this one should be a maybe a quadratic equation because this is a curve, and likewise for this segment here. But then again, it's not really required what is the equation of those curves, and therefore our final answer is already here. So that concludes this video for electric electric circuit, charge and current. Now in our next video, we'll discuss what is the driving force behind why charges flow in a circuit. So I will see you on the next video.